Hi all, welcome back to the webinar or the bootcamp day 2. So in the previous, like in the day 1, we have discussed about the Kalman filter basics, like just an overview, like how the flow works and the steps involved in the Kalman filter. So, and with respect to that, like in the day 2, we are going to make use of the Kalman filter algorithm to implement our like cell model and the cell thermal model. Okay. So yeah, so in the day 2, like as we are going to see the cell model implementation in the state space equation and the cell thermal model development using the lump analysis. So again, like we are going to represent in like state space. So I won't be doing any derivations here. Like already I have like put up some equations in my slides. So yeah, like the final equation how we can represent in the state place and in also a small demo on the MATLAB. Okay. So in the MATLAB, how we can represent that we can go through. At the end, like I have some taken some standard current profiles. So for that, I have like drawn some results. So that results we can discuss. Yeah. So when I say cell ECM model development, right? So we know that like we have like right now like in the market for the two-wheeler sector, like not only two-wheeler, like in all automotive sector, like the e uh, battery electric vehicle are booming. So the cell usage, like maybe the cylindrical, the prismatic, or the pouch, based on the requirement, they have been like increasing. When we say like a cell, for our case, like we'll consider the cylindrical cell right now. So when I say the cell model development, right? So I'm going to capture the behavior of the cell. Okay. Like you take any cell and I do the testing on the cells. Okay. Complete testing. What kind of test? Not something like mechanical test we call, such as like penetration, crash, like and dent, not dent, like crash and on some abuse test, not those kind of tests. So there are some testing which are related to characterization. Okay. So these helps the characterization test helps you to capture the behavior of the cell. So these behavior again we can represent in some mathematical form. So for that I need to represent a cell in a electrical circuit or electrical system, you can say. Okay. So right now, like the one you are seeing over here, it is an electrical system. So we are representing a cell behavior in a mathematical form, that or you can say it as like an electrical system. Later we can bring into the uh, a mathematical form. Okay. So sorry. Yeah. So there is a some standard circuit, we can call it as like Thevenin circuit. So or also we can call it as like 1 RC, Thevenin circuit, or like 1 RC. So right now what you are seeing is 2 RC. Then there is a RINT. So you might be knowing like these names once you went through the poll, right? Like you might be knowing these names. Okay. So here I will just give some like what is RINT kind of thing. So RINT means if this is your like OCV or like open circuit voltage, you can call. Okay. And whatever the resistor you can see are not resistance. And yeah, so this kind of circuit, we can call it as RINT. This is a simple battery model. For this itself, if I bring an RC block similarly like this, okay. So RC is nothing but like might be aware that resistor and the capacitance, okay. So R1 and C1, I'm just giving the name as R1 and C1. Yeah. So this I can call it as like uh, one RC or the Thevenin circuit. So the right now what you are seeing is like two RC. So this is one RC. I'll just change the name to one RC. Okay. So I was mentioning that like about ohmic resistance, polarization resistance, right? So R0 represents your ohmic resistance. R1 represents your like polarization resistance. So even if you take 2RC, like it is there. Okay. Yeah. So just cancel these drawings. So right now, like for this electrical system, I'm applying um, KVL, like Kirchhoff's law. Okay. So once I apply, like I can derive the equations here. So this is U1, like U2 dot and UT. So you can call it as like these voltage across 1 RC, something like this, voltage across 2 RC, and this is like complete terminal voltage. Okay. So UOCV is nothing but your open circuit voltage. So when you measure, like let's assume that the cell, okay, and when you measure over here, you are going to like say in a no load condition, that you can call it as OCV. So if I want to represent this in terms of cell, so consider this as a cell. Okay. So yeah, this I can say it as minus, this I can say it as plus. Okay. Yeah, I'll just say this as plus, and this resistor, capacitance. Okay, I'm just trying to draw the same thing within the cell. Okay. Yeah, something it will come in this way. At the end, like it will end up with a negative sign. Okay. Yeah. So one end will be like positive and negative, that we already know. So once you like try to measure in no load condition at the terminals, we can call it as OCV. When you apply the load and try to measure, then we can call it as like terminal voltage. Okay. Yeah. So once we like get the equations by applying the Kirchhoff's law, and then we have to like bring it to the discrete form. Okay. So yeah, and you can see like if this become the states for our equations, right? So these are like a kind of, or you can say it as coefficients, which is going to sit in the matrix A. If I represent a state like state space A x plus b u, right? So these, the one which I marked in blue, are going to sit in matrix A. Okay. And these it should be like u naught u2, I think so. uh, these are going to sit in the matrix X, and the B, these, and the current, which is the input, which is going to sit in the U. Okay. Yep. I'll just showcase that once I go through the thermal model also. So I'll just go to the thermal model. So here, like a cell thermal model. Okay. So we have been using like a Bernardi heat generation model. Okay. This is like basics of that thermal um, subject through in the engineering. So here uh, we again representing thermal character of the cell through electrical system again. So okay, like using the heat generation model, you can say it as like I square R losses, right? So if I want to define these terminologies, like just let me put this away. Yep. If you take, this is the core of your temperature of the cell. This is on the surface. Here Ri and R naught are nothing but equivalent internal and external thermal resistance of the battery. So you can say it as like thermal resistances. We are representing that in terms of like resistance again. Okay. Yeah. And the last one is like T ambient. And like from further with the Bernardi heat generation model, like we are going to derive like to the cell thermal model. Okay. Yeah. So this Cc and Cs of the equation represents like heat capacity of the battery cell. Okay. When you take up a battery and if you, it will be having some cell, the surface. Okay. And the external medium. Yeah. So Cc is the heat capacity of the internal medium and Cs is the heat capacity of external medium. So it's nothing but like specific heat capacity. Okay. Yeah. Once you have this, like we are going to further take the equation and rearrange with the help of these. Okay. Like Ts is equal to Ts minus T ambient and the Tis equal to T internal minus T ambient, right? And further, going for the Laplace transform, we are going to get this set of equation and then further rearranging the equation. Okay, it should be 1 and the 4, 2. Okay, it should be 1 and 2. And then we get these models. Okay, yeah. Again, like these are going to sit in the A matrix and this is going to sit in a like B matrix. Not these, these. These two are going to sit in the A matrix. Similarly, like these two. Okay. So these TIS and TSS are going to sit in a X matrix. If I take the typical state space, that is A into X plus B into U, right? Yeah. So I'll just try to show you that model. So here you can see that a state space. So the X of K. So I'm just instead of like X kind of a dash, instead of like I'm representing of X of K, and this is of X of K minus 1. So you can see the A matrix, right? So if I just try to compare with the previous, with our cell thermal models, all the stuff, you can see 1 minus of delta T upon R1 into C1, 1 minus of delta T upon R2 into C2. So the same equations have been like used. right? And from these from the thermal. So here we are going to put like the update matrix. Okay, so the calculation, the equation for the SOC estimation. So this is nothing but your basic Coulomb counting. Okay, and then the rest for the thermal. Yeah, and you can be your like current, and these are the state variables. So it is in the transform like transfers. So first state variable will be of SOC U1, U2, TIS and TSS. Okay, so TIS and TSS doesn't indicate any surface temperature or internal temperature. So again, like once we calculate this TIS and TSS, further we know that ambient temperature, we have captured the ambient temperature. So again, we have to subtract from it, subtract or like add it. Then we can get internal and the surface temperature of the cell. Yeah, that too the predicted. So once you like represent the whole thing, like your state matrix, further it is your process covariance. Okay, so these covariance matrix are like I have from some paper. Okay, like they have also approached the trial error method. So of choosing these covariances, the noises and the process like values. Okay, for the measurement and also for the uh, process noise. Okay, yeah, and then like we have to derivative, we have to like derive OCV with respect to the SOC, that we can call it as H matrix. You can call it as like observatory matrix. Okay, and then further like you can bring the measurement equation. Oh, this is your measurement equation where Rk is of noise. Yesterday we already saw the flow. Yeah, and this contains your measurement. So the one like you can say the terminal voltage when you are estimating through a theoretical model, and also the terminal voltage once you are getting from the sensor. So like either from the machine or something. Okay, from sensor you are getting the live data, right? So the sensor data. Okay, and from the machine what you are getting, sorry, from the predicted model what terminal voltage you are getting, that you are going to use it in your update. Okay, yeah, and also the process covariance update. So and like in this way, like the whole like cycle will repeat. So what I'm going to do, right? So right now, like as I said, like I will just try to show you one demo of the MATLAB here. I'll just shift to my MATLAB. Okay, just let me know like if you are able to see the screen of the software called MATLAB or some code. Just type yes in the chat box. Yeah, I'll get to know. I mean, like, just let me know, like you are able to see the screen if you are there. Yeah. Okay. Thanks, Tarun. Yeah. So, like whatever, like I have shown the same consideration I have done. But the thing is that it is in 5 into 5 matrix. Like as I'm using like 5 state variables. So the first step of the code, you can say like initialize. Okay. So it will be like very convenient to understand if the people having some background of MATLAB, like already like have been using the MATLAB. Okay. Yeah. So initially, like, I will be initializing all the terms. Okay. You can see the state variables. Initially, we have to assume the states variables and the initial error covariance, uncertainty noises, initial measurement noise, and Coulombic efficiency. Like I'll just taken as like 0.99. You can neglect it also. It depends. And the QM, that is your capacity of the cell. So right now I am representing in capacity in amp second. That's why I multiplied into 3600. So 2.5 into 3600. So then these are data of the cycle. Just give me a minute, guys. I'm having some noise from my end. Yeah. Yes. So yeah, and then like I have the data. So I have collected uh, the the data, that is like you can say it as like terminal voltage data from live in Excel sheet. I'm feeding the data over here. Okay, and this is my like time, um, and this defines my identity matrix dimensions. So then these CCCS, RI are not. So like these we have to put for the cell thermal model. Like you can say that. Let me go there. So these are not RI are not uh, and CC and CS data. Yeah. So then like I have considered some standard current uh, profiles. So I just you can see all these current profiles. Anyway, like I have drawn some results out of it, and I'll show you further once I go through this code. And then like the EKF loop starts, and like I given like for loop, and I'm going to initialize all my requirements. So in the states I have been like represented. Okay. The only updates I need, that is SOC, like TIS and TSS. Okay. So yeah, and then I had to initialize all my R0, R1, tau. Okay, like R2, C2. So you might be thinking like why these are required, right? So if I go to my model over here, right? So this is my cell like 2RC, right? So we already know that this represents cell behavior. So I captured this R1, R2, C2 data through cell testing. So I'll conduct some tests like HPPC, capacity test, and activation test or something. Okay, through that I get that like the voltage response. From the voltage response, I do the calculation of estimating the R0, C1, C2, R2. Okay, OCV. So I get the data with respect to all the voltage, like from 4.2 to 2.8, or like you can say from 0 to 100% SOC. So I get the data and I represent them in uh, say like I represent that data in like fits. Okay, curve fits. So you can follow like curve fits, however it's comfortable. Like it's not based on comfortable, like it should be on, because if you are going for the more like number of fits, for example, if I showcase over here, so you can see if I take this one, so you can see like 7 degree. So if the number of coefficients and the degree is going to increase, it also affects your in terms of computational requirements for real-time implementation. So there are other like curve fits methods like exponential um, and Wenk's model and many more. Okay. So right now I'm using the polynomial fits. Yeah. So through that, I got all these datas, polynomial fits of OCV R0, R1, C1, tau, R2, C2. So all these parameters are function of some. For example, OCV is a function of SOC, resistance is a function of SOC and temperature. Okay. Right now I have not included any temperature data because we don't have that till yet. So yeah, I have only considered SOC as a function of it. Yeah. And then the derivative of OCV has been conducted and we derived the observation matrix. Okay. Yeah. And then voltage across the RC circuits estimation, that the one you were seeing in the equation, that is like U1 dot U2, right? So these are nothing but like VR1 and VR2. So only the notation is changed. And then, okay, then the terminal voltage estimation. So if you remember these equations, I'm just highlighting these equations. Okay. So just like try to make a note or something. I'll just shift to the next slide. That is, you can compare here the discrete format, like the same equations. Okay. Yeah. Like not this one. So yeah. So once you have like all these data, then I'm representing in a matrix A. Like you can say that um, what we call the state space equation. Okay. So the same like the equation which I have shown over here. Yeah. The A matrix, and I will come back, and the B matrix, and then this is your like state space and predicted uncertainty. Okay. So this process covariance and the error. So this error, we are going to use it in a state update over here. So, and then you are going to calculate the Kalman gain, similar like what you see in the algorithms over here. The same equations like will be used. Yeah. So all these like variables are all already like defined in the above. Like you can see the B matrix, A matrix. Okay. All the stuff will be initialized from here to here, and then we'll be writing our algorithm. So at the finally, we'll be seeing the updates. Okay. Yeah. So this is like something you can say like overview of the MATLAB model. So again, we develop into the Simulink, and further we take it to the code generation. So you can also take MATLAB into the C code generation. Okay. Yeah. To deploy into the hardware. So I'll just go back to the, yeah. So I'll just quickly go through the results. So this was my like current profile, like US 06 current profile. So I am using the current profile from this end, like when there is no charge, because I was initializing my SOC as one. So I don't want to like charge it. So I'm started using when there is a discharge start from here, something over the here up to here. So you can see the SOC and the temperature has generated on the surface of the cell and also the internal. So I don't have like any real-time data like to validate these results. So like I have one paper like once we upload the video in YouTube, I will try to share that link in the video itself. Yep. So you can see the raise of the temperature. Just try to show that paper also afterwards. This is for like US 06 current profile. And then the next one is UDDS current profile. So at some point, okay. So some mismatch. Okay. Actually, this is not SOC curve. This is a wrong one for this. Sorry, for the UDDS. I'll just like correct it and update to you. Yeah. And these are like correct internal temperature and the surface temperature for it. Because as you went in a low load condition at this point of time, some decrease in the temperature happens, right? When you're neither charging nor discharging. That too again depends on your ambient, okay, how it is supporting. Yeah, whenever you're charging and discharging, you can see some slight increase. Yes. So and then like FUDS current profile. So again, from this current profile, I have not included any charging part. Okay, I have only included this one from here, somewhere over here. Just try to represent with a different color here. Okay. So yeah, and then you can see like how the temperature raise has taken. So when we try to measure with some sensors, it won't replicate as you are seeing over here. It may like something you can observe in this pattern. It won't replicate like as you've seen over here. Yep. And this is for the temperature, surface temperature, and this is for the internal temperature. So in the when we talk about like estimating or predicting the temperature through the theoretical model, you see the behavior like this, right? It is because of like I square R losses. So because when you let's say like if I bring a cell model, right? So just getting this one. Yes. Yep. So here is your R naught R1. So basically you are representing a cell model with this equation, and you are getting this behavior according to your how the drive cycle or the current profile. It is because of when you pass a current through your R naught and R1, like uh, when you try to draw the current or like charge it. So whatever the power losses happens at R naught and R1 and even R2. So all this will be added, and so when you like it is straightforward, right? Like Q is equal to I square R losses. So you are just multiplying with your like losses, and then that's why like the behavior appears in this way, the graph. Okay. Yep. So if you see like all other graphs also, you can uh, capture the same behavior. Yes. So I'll just try to go to the MATLAB model. and let me check. Yeah, I'll just try to run. I have included like BJDST current profile right now. So it will take some time to run. It is showing it's busy. Yeah, I got the results. So this is something like terminal test. I don't want. Yeah, okay. Yeah. So all these will be affected. Okay. Uh, how you choose your like values. So it should be like accurate as much as possible. Right now, like for my example, I have chosen some CCCS values from some paper as a reference. Uh, the cell rate, the cell which I'm having over here, the capacity of the cell is completely different. Okay, so as in generally like the materials for the cylindrical cell, most of the time it will be same. Like you take the cell, the CID material and all the stuff. Most of the cases it will be same. So based on that, assuming that all the CS, CC, RI are not will be the same. So I just captured these values from the paper. So if you know, like from the cell manufacturer, okay. So if he provides all these data, so then you can capture the exact results. So what I'm showing is that it is some assumption based, like especially for the uh, cell temperature. Yeah. Yes. So the only thing is that you should have the right data with you.